All right. Hey, welcome everyone to this Disjoint Sets union find algorithm. This is essentially a different version of what was presented in the in-person class in the SD Skills meetup in Seattle. If you have any questions or anything, feel free to message. You will have to be connected to the audio bridge for you to be listening to this message from me and also to follow along. If you are connected through the phone, you may want to log into the app because there's a presentation that Naga will be sharing. Naga, why don't you just briefly introduce yourself and then you can just jump right into the presentation.
Hi, this is Naga, and I'll be covering union find algorithms today. For the folks in Seattle, I have already covered this in person. And I actually wanted to put in a nice presentation, but I ended up finding a very good one online, which is from Princeton University, and they're one of the top universities in the United States. So it's pretty good. So we will go through what union find is and what different variations we have, and what are the improvements and what are its applications, and and we will also code a couple of problems in lead code using union find. Okay. So let me get started. So the first thing, it is given, the first concept before going to union find, which gives a basic, able to visualize union find very easily, to the real world, is the network connectivity scenario, where if you take this network connectivity to the real world computer or internet connected nodes, and if you see in this whole whole dotted thing which represents actually networks, and you have some two nodes somewhere with the black dots, and all you want to know is whether they are connected or not. So for this kind of scenarios, union find fits in very well, and it performs very efficiently, and we will see how. So basically, these are again some real world examples of where union find is being really can be used or being used. It's computers in a network, web pages in the net, it's also used in some transistors and various other things. And when we are actually mapping to the programming model, we often map different objects in the real world to an index, from 0 to n minus 1, if we are really solutioning it for n components. And this is just one picture, and I'll get into that. And we will normally have the 0 to n minus 1 integers gives a quick access, and you can actually, if you are mapping this indices to some other objects strings or some other complex objects, you can have a kind of hash map or a similar mapping to actually map, but the solutions you can always solve using the union find, mapping any object to any indices. So let's get to see what it really is. So before we get into the actual union find, you should be, from mathematics, you should know what a disjoint set is, right? So if you have two different sets, see this scenario, see this example here, 2, 3, 9 and 5, 6, you don't have anything in common. So basically, if you take these two sets and if you do an intersection, they're it's an empty set. So that's a disjoint set. These two are disjoint. So, and let's see how the disjoints actually help in this union find. So let's take that same example, and there is if we want to do like in this union find is like two major operations. As I said, like even if you take to the network connectivity example, all you need to know is like whether they are connected or not. So how do you find if the two components are connected using this disjoint set mechanism? So let's take this example of where like you have 10 different components, and the find query, like if you do find of 2 and 9, so they both are in the same set. So it indicates that they're in the same set. That means they're connected. So that is a analogy that we need to make, like when we are mapping to the real world and versus the data structure, disjoint set data structure. So suppose if you say like 2 and 5, then actually they are not in the same set, which means that they are not connected. And so when you are actually performing union, how you perform is you check where each, I mean, like suppose in this case, like they are performing union on 3 and 8. So 3 is in one different set and 8 is in different set. So they both are disjoint. So when we need to perform union, only if the two elements for which we want to perform union, if they are disjoint, then only we perform union. So that means that we will combine this set 1 and set 2 and form a single set. After forming the single set, we will get rid of these old sets. So, and next time when somebody says like find of 2, 8 or like 3, 8, then they are in the same set. That means that they are connected. So these are the two very important operations like which we do in I mean like disjoint set or union find data structure. And let's get on to the next subsequent slides. So here again they gave a example of this connected components. Suppose say like in this scenario we have 10 different, let's take this as a graph, and if you want to find how many connected components we have in this total graph. So by looking at, we definitely know this is 1 and this is 1 connected and this is 1 connected, 3. And how we actually come up with this using union find, we will find out here. So these are like, if you see the in and out, they are the union operations. That means like initially all of the vertices will be like, imagine like all these are not connected for the first time. So when you do 3, 4, then you only connect these two. So which means that like earlier 3 and 4 would have been in a their own sets, like each element initially will be in its own set. So if you perform 3, 4, since they are in different sets, you are able to perform union. So that's how the output is 3, 4. So then you do union on 4, 9 and 8, 0 here, and 2, 3 here, and 5, 6, which is basically here, and 2, 9. So you see like 2 and 9 are already connected. So 2 is connected to 3 and 3 was earlier connected to 4 and 4 was connected to 9. So which means that 2 and 9 are also connected. They are in the same set. So that's why here the union was not successful. That means that like you didn't really perform union. So because they are in the same set. So and then like you do union on 5 and 9. So these two are connected, but it was not connected with 9. So then you connect it. Then 7, 3. So the 7 was not connected to 3. So you perform this union. So now if you see how many unions we performed, 7 unions, right? And how many components in total we have? 10. So 10 minus 3, which gives us the 3 components. So this is the same logic which you normally apply for this problem. Let me show you in late code. So there is a number of so if you see, if you are seeing this problem, right, number of connected components in an undirected graph. So this is the same logic that you apply to simply return the number of connected components. If you have to write like DFS or BFS, like it'll involve some logic, right? Like all you have to do is just create a disjoint set union or union find data structure, and you simply perform union on all these components like as they are connected, and then like at the end, by the time you complete initializing, you know how many components you have. So far, any questions? Hoping no. So I'll continue. So which is basically, I mean, like this is again abstracting the same way, considering the concept that we have talked using the disjoint sets data structure. So in the same example, take this as u comma v, this as a v. If you have to find whether u and v are connected, all you do is just do a find in the our data structure. What it will do is this find will check whether this u and this v, they're in the same set or not. So basically this find can give the or root or whatever, like what this can also give. So all it basically checks is whether they both are in the same set or not. So it's the same thing. It returns true when they are connected, otherwise false. So it's again explaining the same thing, like union find is a disjoint set of objects. Find queries, all it checks is whether they're in the same set, and union commands, it just combines them like two independent sets into one bigger set. So now we need to come up with a union find, how it will look. So before that, let's look the simpler version of union find, how it is implemented. There are like other variations which we will see. So the simplest variation is called a quick find, and we will see what we do in quick find. So in the quick find, so in all the variations of union find, what we are doing is to visualize all the n components in that undirected graph or like in the real world object. What you do is you map them to an array of n indices, like an integer array. That's what you take. And for each array, you initialize itself as a parent, which means that like for the first time, when you initialize like 0 to 9, you set like the same 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So which means that they are all in an independent its own sets. But in this example, they connected 2, 3, 4, and 9, and 5 and 6. So if you see 5, it's pointing to 6, which means that 6 itself is pointing to 6. So these two are in one set. If you see the 2, 3, 4, 9, 2 is pointing to 9, 3 is pointing to 9, 4 is pointing to 9, so 9 is pointing to 9. So all this, whichever are pointing to 9, they all belong to another set. So this is I mean like now if you want to know whether 2, 3 and 9 are connected, they both have the same parent. So this can be called as a parent or the ID, whatever they have given. So as long as they are same, that means that they are in the same set and they are connected. Like if you take like 4 and 5, like they have different parents and they are not connected. And let's actually see this in much clearer way. It's the same thing, whatever I talked, they are just doing the same thing. To know whether 3 and 6 are connected, they are not, because they have a different ID. So now all these are all connected, and they are all like the connected components. Let's see how we build this data structure step by step. So it's shown here. So this is a array representation and this is a graph representation of how we build a disjoint set or union find data structure. So here it's actually, if you see the first step that we are doing, here also it would have been 3 before this step. So here they are doing a union of 3 and 4. So which means that you just made one of them pointing to one of the objects. Like you can also do 3 as a parent and 4 as a child. So there is no problem. The main goal is to group the components, not deciding which one is a parent or which one is a child. So in this case, it was decided 4 as the parent, and that's how we updated the index at 3 also to point to 4. And now we are doing like 4, 9 union, and then so if you see, 3 was earlier pointing to 4, and since we added 9, all we did is we want to make all the components within our connected area to point to 1. So we could have picked 4 here. So in that case, we can put 4, 4, 4 here. But like in this example, they picked 9. So that's why they just put 9, 9, 9 in all the 3 places. And you can see here 9 as a parent and 3 and 4 are child. All others are still not connected in their own sets. So next they connected 8, 0. So now you can see, since 8 and 0 are like in their own independent zone, we can either do 0 as a child or 0 as a parent. In this case, they picked 0 as a parent, and that's how they pointed 8 to 0. So since 0 is a parent, 0 is a parent here and 8 is the child. So similarly, if you see 2, 3, they made join here, and 5, 6 again they pointed S6 as a parent, and 5, 9. Since like if you see the 5, 9, 5 and 6 are in their own set, and 9 is in different set. So every time you do a union, what you do is which set each element are. So 5 is in a different set, 6 is in a different set. That's how you perform the union. So in this case, 5 is in a different set, 9 is in a different set. That's how you are doing a union on these two. So in this case, I decided 9. They decided like 9 as a parent, and that's how all this became 9. So the next they did like 4, 8, and then finally 6, 1. So finally, if you see, since they decided 1 as a parent, they ended up changing everywhere. Like here, they ended up choosing 0 as a parent. That's how they ended up changing all the places wherever 9 was there to make it 0. So at the end, you see all are connected and all are pointing to 1. So here is a quick implementation of how, in Java, how you implement this. So all you do is like you have an integer array with size n. It initializes, in the constructor you initialize the parent. You can call this as ID, or more like logical meaning as a parent. so you know that like they themselves are parent. And in the find, what they're ultimately doing is whether the ID, I mean like whether the parent of P is equal to parent of Q. So in that case, it returns a true. In the union, it just picks randomly like the parent of P and checks wherever the parent of P is there, update itself to parent of Q. So that's how you ended up seeing all the elements being changed here, like step by step. The parents are keep getting changed. So this is the simplest one, not an efficient. And the reason why it is not efficient is, you see, like you in the worst case it will end up being n operations. Like whenever you are doing an union, so you are end up changing the parents for almost most of the elements towards the end of the array. So the time complexity is quite big. So that's what is given here. If you see, like n is the number of objects. If you perform m union, like it is this slow actually, if you see. If you have to do like 10 to the power of 19 operations, it will take 300 plus years with that algorithm. I mean, like, I think now with the powerful computers, it may be faster. But like in those days, it is like 300 plus years of time, which is very bad. Any questions before we go to quick union? There is a simple modification. They come up with 10 to the power of 9.
Can you repeat the question, Atul?
Yeah. Because there were 9 elements. No. I think that was just an illustration for a large inputs, how that quick find will actually perform in the runtime. I mean, like they just took for some machine where they were calculating the performance. If you see, it is not related to our specific problem. They're just in general talking why it is slow, and the approximate statistics proving it is that much slow.
Yeah, for a very large element size where there are 10 power 9 elements, then you will need 10 power 10 edges, because that's what is connected. Then total of operations for quick find will be 10 power 19. So that's 300 plus years of computing time. So this is assuming 10 power 9, which is essentially 1 billion elements, right? That's just the data set they're looking at, nothing more than that.
Okay, and another question from Nisha is like, how do we decide which elements to connect? Is that given in the input? Yes, I mean, like we sometimes it is given or sometimes it is indirectly given. We need to figure out how we are connecting. I mean, like we'll take a like data structure, or like if you take the network connectivity analogy, like in the internet, as long as whenever you are connecting one computer or intermediate node to an internet, so then I mean, like whatever to the existing node that is there to your new computer which is getting connected, you perform a union. So you know that your computer is also connected to the internet. So that's kind of a real life analogy. So that means that whenever some new input is coming and being associated with another input, then like you decide to perform union, and later to know whether they are connected, then you perform find. We will see some coding examples also to get an idea.
So Naga, I have a question before you move.
Yeah, sure.
Yeah. Just move to the previous slide. Little bit.
Okay.
Yeah. Actually, what is the role of that edges here? Actually, as per the previous example, I understood like if 10 power 9 nodes are there, then we have to iterate all 10 power 9 element and we will try to update the parent based on the
Yeah.
union what we are performing. Here the edge has really any influence in the algorithm or calculation?
Yeah, correct. So whenever you are performing a union, like which means that you are connecting those two nodes logically. So you're adding, I mean, like that's how there is a graph representation to depicting every union operation, right?
Yeah.
So every step you perform a union, you are adding an edge between those nodes in a graph, pictorial, like.
Okay. Okay.
So that's how, like, if you end up connecting 10 components, all of them are connected. That means that you have n minus 1 edges, like if which is 10 minus 1 edges. So in this case, if all of them are connected, then it will be really like 9 edges.
Yeah, but here it is saying 10 power 9, 10 power 10, right?
No. I think that is not related to this example illustration. That is just, I think, what they are trying to. This is a very simple version of quick find, so which performs dead slowly. And I didn't actually cover this in the class actually, because so we use an optimum version. Yeah.
Actually, so the way to look at this is that these are two different data points: 10 power 9 nodes and 10 power 10 edges. Right? Each node is connected to some number of nodes, right? So you're saying that on an average, let's assume that every node is connected to 10 other nodes.
Okay. Okay.
That's 10 power 10 edges, right? Okay.
Okay. Okay.
So that's kind of what we're looking at. Maybe like.
Yeah, that's fine.
That's what it is. There's a bunch of questions from Nisha Naga.
Yeah. So yeah, I'm just looking at them. So for internet computer, say my home will connect to my router, which has public IP, and router is connected to probably ISP. So if I consider my computer as a node, am I performing union with my home router? Yes, correct. Yes, that is correct, because it indicates that your computer is connected to your router. So, and your router was already connected to ISP and other components. So you ended up logically connecting to all the ISP and whatever the public IPs or whatever the sites your ISP is aware of, you should be aware of from your computer. I think that's how we ended up reaching all the examples. Okay, so let's look into the next version, like which is so all the variations that we see here, they all have the union and find operations, but there is a little change in the terms of code, how we picturize the graph and what decisions we make during find and union differs actually between everything. So this is a little better than previous one, but let's see what the problem with this also later. So in this case, it's called quick union and it's little lazy approach. So every time, instead of updating all the nodes whichever connected, here you simply point to another parent which is already there. So in this example it may not be clear. Let's go to that illustration. So if you see, until the for an I, until the parent is itself, you keep going. So that means if somebody says 3, 5, you don't directly link. So you keep going until you find 9. So you keep going until you find 6. Then you perform union on them. So let's basically look into the actual example here. So here, as given in the previous example, initially we perform union on 3, 4. So in this case, you can see third index is being updated to 4, means that it's pointing there. And next time you are performing union on 4 and 9. So if you see here, you just updated the parent of 4 to 0.9. 3 is still pointing to 4. So if you see here, 3 is still pointing to 4, all you did is you just updated 4 to 9. Whereas in the previous example, what we were doing is we were changing all this 3, 4 and 9 point to a single one, which is 9 or 4 or 3. But in this case, we are not updating for all the nodes. We just change the nodes which are like connected. Like in this case, 4 was updated to point to 9. So next example 80, because they are all like independent here in this. So they just we decide any one as a parent and you connect. And next you are doing 2, 3. So 2 is separate and 3 is within this set. So when you are performing union on this, you see you only change 2 to point to 9. So not all other nodes. So only 2's index is changed to point to 9. So that's how you see in this graph also. Next we are connecting 5 and 6. And then 5 and 9. In this case, you see 5 is in different set and 9 is in different set. That's how you ended up. So you are not directly pointing 5 to 9. So you go to the parent and you link its parent to point to 9. So whereas in the previous example you are very dumb and every time you are updating all of them to point to 1. So in this case it's kind of coming to a graph kind of scenario. A realistic tree kind of graph.
So then here, one question. So then here all union not going to be order of one operation?
Yes. So in this case, the union is not really n operations, but there is some other problem which we are going to come up. I will just show here now. So next you perform 7, 3. 7 was separate and 3 is here. So all you do is just link this to 7 to 9. So it's parent. So they're all in the same set now. So next you join 4, 8. So 8 and 0 are in a different set. So in this case, you simply make, so all we are doing is we are randomly picking the parent. So we are not seeing like this is a bigger tree and this is a smaller tree like that. So you just simply change, in this case, 9 to point to 0. And that's how you performed union on 4 and 8. Because 8 is here and 4 is here. 4's parent is 9. 8's parent is 0. So you just perform union on these two. So which means that you just link one of the parents to other. So which means that like I'm making 9 to point to 0. So at the end, we want to do union on 6 and 1, which are again in different sets. And I randomly pick 1 as the parent again. So which means that 6 parent is 9, 9's parent is 0 earlier. So 0 is the main parent of all. So you just simply point to 1. So in this case, at the end of all the unions, you see 1 is a master parent of all the nodes. I mean, like, but in reality, what we need to see is like whether they are all connected or not. That is still the main goal of union find or disjoint set. So as you see here in this approach, our tree is getting taller, which means that now if you need to find 3 and 5 are connected, you keep checking 3's parent is 4, 4's parent is 9, 9's parent is 0, 0's parent is 1. So similarly, you all the way check for this 5 also until you hit 1. So yes, their both parents are 1, which means that they are connected. So if you see this tree height, it's almost getting closer to n. So in the worst case, the height will touch n in this variation. So if you this is the implementation. If you see, the find also uses this root and union also uses this root. So this root simply gets the in each level what is the like root of 3 gives 1, root of 5 gives 1, root of 9 still gives 1, 8 gives 1. So that's the idea of root method. And find, you simply check whether these two are connected. So you get root of this equal to root of this, then they are connected. So in the union, you get the root of both and you simply update the parent of one of them to point to another. So there is no logic in updating the parents. You simply update. So the main logic here is like until the I becomes itself, which is the goal, like 1 is equal to 1, which means the 1 is the parent of all, then you return 1. So until then you keep updating I to the parent of the current I. So that's how this root function works. You can also simplify and put this root logic inside find, and you can make union to use find. So there is, I mean, like this is also fine, and if you just implement all the logic within find and union, that is also fine. So the main goal is you should have the goal of connecting in the union only when their parents are not same, and the find job is just to tell what its parent is or whether they are connected or not, as in this example. So again, taking this quick union look also, it becomes expensive because the tree sorry, this is the previous one. Quick find effect is that it takes every time n steps mostly, and but this gets vertically, like, which means that the height or depth becomes as close to n. So let me see if there is some question. No.
And Naha, I have one question. Just
Yeah,
for my
tell me.
clarification, the quick find, at least it is always better in finding. To find that we were having always order of one operation, but the second one looks like in worst case both can be order of n. Is that right understanding?
Not really, but this is also, I mean, like in the case it can hit n. So if you see, it's using this root, which basically can go to the depth of the tree, this root. So you are hitting the depth in both find and union, yes. In the previous, like the union was worst. So yeah, here the find is always one operation, but union is always n. Yes, you are right. So here, though we improved little bit, I mean, like we still end up with the worst case scenario of the going to the depth. So
Okay.
so here is a comparison. So here also, since we are using find, that's how we are getting close to n. So the next thing is, what are the possible improvements that we can do? So we can actually, if you look into the previous example, we can, so here whenever you are performing union, you are randomly pointing one to another. So in this case, those 0 trees are smaller and 9 trees bigger. You are still, I mean, like pointing 9 to point to 0. So instead, one possible improvement that we could do is add weighting. So which means that we can we add another I mean, like another array to keep, or like the size to at each level. So let me show you with an example here. So the same example, if you see here now, for the first time it didn't matter because both 3 and 4 have the, initially all the size will be 1 and they will be pointing to themselves, and in this case like 3 and 4 are joined, which means that like since their both size is same, it's, you can call it as a size or rank or weight, all it means is the same. It just you're just keeping track of how many components are connected to that. So when you do 4, 9, you know that 4 set is size is 2 and 9 set is 1, which means that 3 is a bigger one. So you attach 9 to child of 3. Similarly, 8, 0 doesn't matter because they're separate, and you can make any one like 0 also as a parent or 8 as a child, or the other way, it doesn't matter. But when you do 2, 3, 2 is 1 and this is size is 3, and that's how you made 3 as a main choice. And in this case 5, 6, again they're independent. And then when you do 5, 9, so 5 is size is 2 and 3 set size is 4, which means that this is smaller compared to this. So you simply point this to a root of this, which that's how it is done here, though you are actually performing union on 5 and 9. And similarly 7 and 3, so 7 is separate and 3 is a bigger set, and that's how you end up linking. So 4 and 8, again you still link to 3, and 6 and 1, finally you end up with this tree. So now with this approach you see almost they're almost flat. So this is one of the improvement, and it's called a weighted quick union, or you can say union find by rank, or union find by weight, or union find by size, or weighted quick union. All means the same thing. So programmatically what you are doing is, in addition to having a parent pointer like ID, you are having a size counter also to have the count of the elements that it has. So find is similar to the previous quick union. So what we are doing is just modify the union to check the size array, additional size array, and the size array you will at the first you will initialize to 1. So let me actually, I think there is no code, but we can, they just given this component. So this logic will be there in the union with the same previous logic here. So here we'll just have additional size logic. We will also code this. I'll show you in lead code how we can do union find by weight. So if you look at the analysis, this is almost like a login. So, and how it's login, I mean, like it has some proof, but it's definitely a lot of improvement over the previous one. Oops. And this weighted union also, I mean, like sometimes this, I mean, like this login can be further improved with the technique known as path compression. Let's see what that is. So in path compression, if you see if the tree depth is like this, I mean, like you even avoid these levels as much as possible in the path compression. But like in weighted union, this may be possible, all these kind of trees. Let's see. So you just add this logic to make to get the path compression benefits. So in the root method, all you do is at every step you are finding the parent of one node, you keep updating the parents also. So all you are doing is parent of I, you are updating to parent of I. So earlier we just had this logic until we are finding the parent, we keep looping. Now as we are doing that, we are also updating the parents. That means you are reducing the levels as you find the parent. So this path compression technique keeps almost flat, almost like completely, it's almost very negligible that you have a nodes even in the second layer. So with this, the find or any operations will be almost like very constant time. So this is called weighted quick union with path compression, and given this login proved like almost like a constant. You see here with n increasing like exponentially, and what this log star n is. It's not really log, but it's yeah, some kind of constant. Even if it's so big, you can still get it in within 5 levels, even if you have this many number of nodes. So in theory, it is not really called like a linear or constant, but in practice, I mean like this algorithm, in practice it's almost performs like order of n. So this is the overall summary of the time complexity. Any questions before we go on to practicing some problems or coding some problem? So if you look at to the previous practical problem where they're comparing the analogy. So with this technique, which was executed using the previous algorithm like in 3000 years, can be executed within a minute using this algorithm. So it makes it possible to solve problems which otherwise they thought as couldn't be solved.
It's not something related to this concept, but just I'm curious. Is there a way to find out this calculation number, whatever they have given? 3 years, something they are saying, right? It means.
So you need to actually run this the same program that we have, right? Okay. Create some test program which can flood as this many components, I mean like 10 to the power of 9 nodes, and connecting having this many unions. Then you can have a program that measures the time before and after, right? With the both algorithms, you can have the other algorithm and you can have this specific algorithm, and you can compare, right?
Yeah, basically. I agree, but I am little bit curious, like no one might have allowed this logic to execute for 3000 years, right? There may be
no, I mean like there,
right?
Yeah, I mean like we really don't know the history of this, right? Like maybe in 70s somebody come up with quick union, and then later in 80s somebody made some improvement. So in the previous days we really don't know the history of this, how this invention came up.
Oh yeah, thanks. Yeah, thanks.
Yeah, no problem. So even with the binary search, they said like almost 10 years nobody noticed the bug, and then there was some update of how we do binary search logic, right? So maybe similarly they also noticed this.
Yeah, okay. Because my main concern is whenever we are seeing this number, is there really some solid way to do or get that with math without using the running the program like that? That's where I was curious.
Oh, okay. Using some mathematical calculations.
Yeah.
Okay. I think maybe as they said here, like I mean, like this is how they compared with real to n and this log star n, whatever it is. So this values, this is how they compared. So this without like really running this program, they would not have come up with this number. So proof, as they are saying, like maybe mathematical proof is difficult, but programmatically, I mean, like executing wise, maybe I think they can prove. Yeah. Let's see, somebody posted some question. Weighted quick union is using the size of the tree to decide which should become the root. Yes. So even the with path compression also it uses the same logic, but it has additional logic in the root. So this is the only addition even in the path compression technique. Otherwise it's almost same as weighted quick union. So with this union, like so whenever we are implementing, we should try to aim for this weighted quick union with path compression logic, so to run efficiently, because this is a very optimum. So yeah, let's come back to this, quickly wrap up with this applications again. So it's used in wide variety of applications. Like one example we already looked, like network connectivity. There are some techniques called as percolation, image processing, and least common ancestor in trees. And there are, like, even as I said in the in-person class, it's used for minimum spanning tree. Just if you have cycles, you can avoid them using union find, because our find or union will always return false as long as they're in the same component. Yeah, they just gave some real life examples. We don't need to go and learn all that. So maybe if somebody asks, we can just specify that it has good practical applications. So any questions before we pick some problem? And
sorry, one quick question. The least common ancestor, so by traversing the tree, we have to create that union set? Actually, I couldn't quickly come up with some solution for this least common ancestor using this union set.
So least common ancestor, so basically least common ancestor is the root of the current node that you're looking, right? So if you are looking like two, I don't know, so let's look into some practical tree to get an idea. So if you see in this case, like whether the least common ancestor of anything is basically 3 only for both. This may not be the right one to look at.
But actually ideally root common ancestor we have to take a normal tree which is not following this union. So and from that, how can we come up with a solution by using this disjoint union set? We have to find out, right?
Yeah, I think maybe what I think is, like, you try to emulate those edges by connecting this root and child, and then at some point they both will return true when you try to attempt union on those, because they are having the same root.
So it means we have to build the disjoint union set by traversing the tree first, then only we can attempt that. Is that right?
Yes.
Oh, okay.
So even I need to try that out. I haven't tried, but like similar problems we have seen, right? Okay, with this, let's go on to some problems. So in the classroom, I solved this is a graph valid tree. If we want, we can still pick the same, or if you want to pick some another one, I'm happy to do that.
Whatever you pick, maybe you can pick any locked problem. I guess unlocked anyone can take.
Yeah. So let me show then like the same example. I'll quickly show, and then we can, if you have any questions, then we can go. So I have already coded. Maybe if you want to code freshly, I can do that. Or if you want to have a look at the implementation of what I have, union find. So if you see, this DSU is a disjoint set union, which I created a data structure. I have a parent integer array, and it passed a size. I just initialize, and initially I set the same index as a parent for itself. And I have two operations, find and union. Basically, I put that root logic within find, so I don't have an additional method here. So while it's not parent of itself, then I mean, like, this is actually with path compression. So
level, can you explain the approach, Naga? Because you are actually before going
which
to
approach?
disjoint set, just can you explain how you are
Oh, okay.
The explanation.
Yeah, correct. So the problem is, let's go through the problem. Sorry, I think I confused you people directly by going to the solution. The problem is, given a graph, tell whether it's a valid tree or not. So in this example, there are like 5 edges, and you see that like 0, 1 are connected, and 0, 2 are connected, and 0, 3 are connected, and 1 and 4 are connected. Basically, 0 looks like the parent of all 1, 2, 3, and 1's child is 4. So it's still like all are connected, and then the result is true. And basically the idea is, graph will be a tree as long as all the components are connected, and the number of connected components are like, if you say 5 components or 5 nodes, then 4 edges should be there in your graph to become a tree. So I mean, like, since I don't have a pictorial representation, I can use one of this.
Okay, all should be connected and the loop should not be there, right? Maybe these two.
Yes.
Okay.
So if you see this example, like any of this, they are still a graph because they are like unconnected components. In a graph, you can have this kind of a graph, but it is not a tree because all these are connected, but these are not connected. So we don't have a cycle here, but this is still not a tree. But if you look into the last one, this is a tree because you have 10 nodes, and if you count the number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 minus 1, which is 9. 9 edges should be there, and there should not be any cycle. Then it's a graph. The same logic I am applying here. I mean, like, we are going to do using union find, basically.
Okay, so you are creating the disjoint set. Finally, if we are getting only one set, then you are saying all are connected.
Yes. Right? So what I am actually doing in this find and union is, this union will return me false if they both are pointing to the same parent. If you see, I have a find logic in this union operation where I am getting the parents for both nodes, which I am going to pass. If they are pointing to same, I am going to return false, and I am using that logic here. Like, these are the list of edges, right? Like, so whenever I perform a union, if they are in the same set already, and you still need to add a edge, which means that it's resulting in a cycle. So basically, even if the problem is to find a node using which basically let me show you the other problem where there is a cycle logic. So in this case, if the cycle is there, then you return false because it's definitely not a tree. And if you are able to perform union on all the edges, then the number of edges should be equal to n minus 1. So as I said in this example, if you have 10 nodes, you should have 9 edges. And for the cycle analogy for others to just visualize, imagine like 4 and 8 are connected in this, resulting in a cycle. So in that case, it won't let you do union in our union data structure because we cannot do the union as long as they're in the same set. So is it clear to everyone? So in this example, if you see, there is a cycle because 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, and if you see 1 is connected to 3. So there is a cycle between 1 to 2, 2 to 3, and 3 to back to 1. So that's how our logic will return false in this scenario.
So all are connected or not, you are doing with simple math, right? It should be just edges of length should be n minus 1. There is no logic. Or
yes, yes.
Only
there is
to
no
find
logic.
the loop, you are using our disjoint set logic.
Yes, and in that process, yeah, correct. So if there is something is not connected, then you will, like has a cycle, it will result here. And if something is not connected, then definitely the number of edges won't be equal to n minus 1. As you can see here, if something was not connected, even in this case, if you take this example, then the number of edges will be 8 and the number of nodes is 10. So that logic will fail. So this is not a tree. So this is the logic and this is the path compression technique. And let me basically go to another problem where I can spend some code. So the other one which I was talking about, right, the cycle. So this is the problem which is called redundant connection. It's the similar logic. Here what the problem it says is you have a tree which is an undirected graph and it is connected and has no cycles initially. But at some point somebody added an edge. So they're adding an edge which is resulting in a cycle. So it's a graph with 10 nodes with one additional edge added. So the added edge has two different vertices from 1 and n and was not an edge that was already existed. So the resulting graph is basically a 2D array of edges, written an edge that can be removed, so that resulting graph is a tree of n nodes. If you have multiple answers, you can return the first one. So in this case, let's look at the example they have given. So in this case, 1 and 2 initially they are connected, and 1 and 3 they are connected. These two edges are fine, but adding this resulted in a cycle, so not making it a tree. So they are basically asking to return this edge. So in this example, adding 1, 4 resulted in a tree. Sorry, cycle and not making it a tree. So it's the same logic as the previous problem, but here what I am doing is, as soon as my union returns a false, I know that that is the culprit which caused it not making a tree. So that's how I'm just returning the same edge as soon as I get this as a false. And so DSU implementation is the same. Oh yeah, I think maybe I can use this to demonstrate the rank. So the size or rank example, I mean like it's not required here, but I have in this example.
Naga, sorry to interrupt. I think one
Mm-hmm.
guy asked a question like 2 to 3 also can create the loop like that. But I think you are trying to return whatever the first edge creating the loop, maybe. Is that right?
Yeah, correct. So yeah, Adar, I think to answer your question, the problem in lead code was add the edge which resulted in a cycle. So before adding a 2, 3, it was not a cycle. So just don't visualize this. So if you don't visualize this at this step, if you are just added these two edges, then it is a valid tree. After adding 2, 3 only, it resulted in a cycle because you need to go in a sequence, right?
Can you scroll a little bit down, Naga? I think his question is
In
regarding
the
the
problem.
second example. Yeah, second problem.
Oh, okay. So 1 to 2 was connected and 2 to 3 is connected and 3 to 4 is connected. So if you don't imagine 1 to 5 and 1 to 4 edges, it is still not a cycle because all you did is 1, 2, 2, 3, 3, 4 connection. Only when you add 1 to 4 connection, even before adding 1 to 5, this is the one which resulted in it not making a tree. So that's how we returned only that 1, 4. So in this example, so as soon as our union returns a false, which means that both parents are already same. In this case, if 1, 2 and 2, 3, 3, 4 are connected, then all these 4 nodes are in the same set. So when you do union on this two, you know that 1 and 4 are in the same set. That's how you know the cycle in this using this union. Just to quickly demonstrate, I think you already seen in the PDF, but I just have here a similar rank. You can even call it size or weight, whatever it may be. And then actually I can even I should have initialized this with 1 actually, but it doesn't matter because because each one had one component. I should have initialized this with 1.
So here you implemented without path compression, right?
No, you see there is a you are updating as when you find you are also updating the parent. So when you are updating the parent, which means that it is doing path compression. If I simply say x is equal to, instead of this, it is not path compression. So this is also valid, but it's a weighted quick union. So this is a weighted quick union. Whereas if I do this, it becomes, you can actually call it recursively, or you can also do 2 loops like parent of parent. You can, like this also you can do, which is an iterative way.
Okay.
So both are same thing. Just to be logical, I just gave a find, not to confuse. And this can be either one because both will be the same. Because when they both equal only, you return. So this is a weighted quick union with path compression. So as you see, like you get, you find what their roots are. If they're same, you return false, saying that you cannot do union. Otherwise, you check the rank of this parent and this parent. Whichever is less, in this case, f of x is less. That's how you point this parent to the fy, which is greater. In this case, otherwise. If both are same, you can pick any one. It doesn't matter. I don't know what was the test case I executed. I think I did screw something. Two, three. Yes, it is. Since I'm using find function.
But maybe it is not the thing what we are. It's not doing because X. If you are updating, then we are not updating the parent, right?
I think, yeah. Let me see.
Maybe you can see if it is working fine. You can submit and see the time difference. Maybe it should be more than your previous submission.
You want to compare the time? I don't know what my previous.
But I don't know. These people really giving the right time.
Accurate.
Yeah.
So, but I think this should work. Wait 1 minute. This is a path compression. Let me.
You can see what is the error say.
I think this may be correct.
Just expand your error log screen. Maybe you'll see what it is saying.
Its screen? No, the error is because it's getting past this edges. Basically, it's getting past this union step.
Oh, okay. It means one test case is failing.
Yeah, I think it's little curious. I don't know why it's ended up. Let me see. Yeah, I think I changed this to be when I had a different scenario. I changed this, right? Sometimes you have x is not equal to the other side. So I think because of this statement,
yeah, because we are stopping. Okay.
As soon as it is
not equal, so it is not returning the value what you are expecting, maybe.
So yeah, so this is again with path compression because we are updating it. Oops. Again throwing for some example, I don't know.
Or else maybe if everyone is okay, maybe you can take one problem, remove all the existing code, whatever you have written, maybe you can start from fresh.
Yeah.
Better if everyone is okay. You can do
it. Shall we solve the problem which we haven't solved, or what shall we do? As the next one, I can show some different. I was thinking to show a different example. So let me see, some people are posting. Yes, this is what I had previously, so I'll switch back to this. It's accepted. So hope everyone got the idea, right? Like different problems. So let me go to the again back to the union find. Just to I don't have a shortcut to go back to this union find. I'll keep this. Oh, I think I have here. The number of connected components, as we saw in the problem, I think it should be straightforward. Just like counting the number of components. Let me see whether I have coded for that or not. I think I might have already solved that. Yeah. So if you see here, I have the similar DSU structure. All I am doing is I am counting the number of unions, and when it becomes true, which means that you are truly performing unions, and then you simply do n minus count. It gives the number of connected components. The same logic applies to this number of islands first problem. But here, I mean, like I solved using depth first search, but instead of this, I could have used the same DSU structure and count the number of unions, and just to minus of the number of unions, you should get the number of islands, even in this scenario. Whenever there is a 1, you just need to do a union on I and J. But I think for this to work, you should clearly map each vertices to approximate index numbers. Otherwise, you will end up in a. I will
Can be
show.
solved using DSU. If you maybe you can try to solve if everyone is okay, right? Do you think it can be solved easily in using disjoint set?
Yes, we can solve it. I think there may be a solution which might be posted also. If you want to.
So first, you can discuss the approach, maybe how you are thinking. Yeah. To solve it. Yeah.
So I think the idea is, let's go to the 2D grid. Ones and zeros. An island is connected by water and is formed by connecting adjacent lands connected horizontally or vertically. So basically, the idea is, since it's not n by n matrix, it could be m by n also. So in that case, we will have to have like m into n. If this was like m is like 5 and n is 3, then you should have 15 disjoint indices. Like with each wherever there is a 1, then you know that like with those specific ones you can actually perform a union between I and J. And you definitely need, let me show, I think we solved the other one, right? Islands too. Let me show that example to make it clear how I am mapping the indices. It's the same problem, a little incremental problem, and it's a hard one. And so here it's a like they just increase the complexity of the problem. So here all they said is find the number of islands. That means that here all ones are connected horizontally and vertically. So that's how the number of islands is 1. But in this case, these 4 are connected. This is on its own island because there is nothing horizontally or vertically for this. So these 2 are again connected. So there are three number of islands. So in this second problem, if you see, at each step he is adding some ones basically. So initially all the matrix is 0 filled with water, that means no island. So he is adding add land at 0, 0 index, and then we need to return the number of islands, which is 1. And then he is adding at this step, these 2 are still connected, and the number of islands is still 1. And the next step he is adding 1 in this place. So now these 2 are connected and this is on its own island. And in this case 3. So at each add land operation, which is basically he gave the this at each increasing step, you are doing the at each and every step of this positions you are actually calculating and returning. So you need to return in a list form. So just see like how I mapped here. So I have the M and N matrix. So I'm basically creating a DSU disjoint set of M star N, and I'm also having a logically matrix just to set the ones accordingly and count at each and every steps. So I'm going through these positions one by one, and let's get to this actual logic. Essentially I have the count as 0, and this add land I actually get the positions of this whatever is there here, basically 0, 0, and I set that in the matrix. And then the row and column neighbors, I am just having a shorthand form of column neighbors and row neighbors, which is basically you go for this is a neighbor, this is a neighbor, this is a neighbor, and this is a neighbor. So for all those 4 variations of places, I have this, and I actually loop. I check whether each indices is valid here by taking this index, which is from the positions, and I also add all these neighbors. And if this is valid, and if this is 1, then we know that like we are going through the neighbors of this component which we set. And even if the neighbor is 1, then we need to connect those 2 to logically. That means that we need to add union on that. So initially we assume the island as 1, but if you are performing union, so you are connecting to an existing island, that means that you need to decrement the islands. So if you perform like 2, 3 unions, then like you are making 2 surrounding components point to an existing island or existing connected component. That's how you decrement 2 times. So you return the -1 here if needed, or whatever the result, and then you add that to this count, and you at each step you add to the result. So there could be a scenario like after this step I could add a 1 here, making all of them as connected, and it should return 1. So let's run this code and I can show you that example which I talked about. It's returning 1, 1, 2, 3, right? So which is basically the second one. So let's add a edge at, is it like 1, 1? Yeah. So at this point we should expect all of them to be connected. So in that case it should return 1 as the last number of components. So you see, this 1, and we are also returning 1. That means that like in this add LAN step, it returns a -2 for the third scenario because it performed union on the existing islands. Any questions so far? Sorry, I think I actually solved most of these problems and my lead code have the solutions already. So let me see.
Hope you will share that PPT, right? Whatever you can.
Yeah, I will share.
Yeah.
And I think in the class I also shown this, basically this example. So this is another non-integer example for the folks who are new, like for them it may be helpful. So in this, if you see, the problem is they have two sentences. Basically the first sentence is basically great acting skills, and the second sentence is fine drama talent. They're saying like they are similar. There are like the similar pairs using which you need to add the relation. So they're saying great and good are same, and fine and good are same, and acting and drama is same, and skills and talent is same. So in this case, since great and fine are not directly related, if you see, great is connected to good and fine is connected to good. So that means that they are connected through some other component which is good. So they are saying the similarity is transitive. So if great and good are similar and fine and good are similar, and great and fine are similar too. So in this case, you need to compare these two words and return whether they are similar or not. So let's see how I actually solve this using union find. So one of the quick examples, or like we know, is like if there are like additional word in any of them, or the length doesn't map, then we can straight away return false. Otherwise, all we do is go through all the list of pairs, and for each word have an index in our union find data structure. So that's what I'm actually doing. I'm just having an index and mapping each one in a hash map to a string to integer, and I initialize with the total capacity, which is now at this point the index, and for each pair then I simply perform union on all the pairs. So when you perform union, whichever are transitive relation, like in this case great and fine were not directly connected, but through these unions they will be in the same component. That's how it actually helps. So once you have once you perform union on all the pairs, it's straight, and now you also know that the both are of the same length, since they are given like in the form of string array. So as long as the words are equal, we know we can keep continuing, and if the word doesn't match, we need to see whether sometimes like this words, like if I have something X or D or E is here which is not there in the pairs, that means that it is they are not equal. So if they don't find in your map, which means that they are not in the disjoint set and also not equal here, that means that they are not equal, so you can return upfront. Otherwise, what you do is you get the index of both the words and check whether they both belong to the same parent or not. So you just have a find which gets the parent of both, and if they are not same, then they don't belong to the that means that then they are not similar as per their definition here, so we can return false. Otherwise, like, we can return true. So it's the same data structure again we are using. So it is in general, I mean, like, for the interview purposes, I think it may be okay if you write even not an optimum one with path compression and weighted one. I mean, like, here it demonstrates the path compression, but not by weight. So, I mean, like, as long as you implement the DSU data structure and use it, or like union find and use it, you're good. Let me see. What property makes this union find problem? If it's already known by category. Okay. So, yeah, I mean, like, that's a good question, but in general, what I see is most problems which you can think of in terms of graph or like associated like to the connectivity or transitivity, like, or indirectly related or directly related, or like in the form of connection or in the terms of graph connections. So then it's a good candidate that you can use union find. So for most of the graph problems it applies, and whenever you have transitive relation, as I said, or you have the connectivity or number of connected components, like anything associated to the connectivity and the relation between two nodes, as long as you are building a relation with multiple nodes with one another, then that relation can be best described in the form of union find. Basically, whichever are related, you are grouping them in a one set. So that's how you logically associate them. So any questions? Maybe we can just wind up little early.
Yeah, thanks, Naga.
Yeah, no problem. Any questions, folks? I'll share this slide basically after this session. It's a very useful slide actually.
All right. Hey, thank you everyone for attending this session. I will the recording is actually in play. So what I'll do is once the recording is complete, I'll upload this on YouTube. And if you have not done so already, please join the Slack channel that we have, which is sdskills.com/slack, and we actually discuss these questions and a lot more on a pretty regular basis. So. Thank you everyone for participating, and special thanks to Naga for patiently going through each one of our things and the questions. Thank you so much.
Okay, thanks everyone.